Hi there, and welcome to this lesson on Further Pure Mathematics 2. And in this lesson, we're continuing to look at loci and complex numbers. In particular, we're looking at loci of the form, the argument of z minus z1 is equal to theta, where z1 is a fixed point in space. And that's saying that the angle between a point and some fixed point is always equal to a constant angle theta. What that gives you is an infinitely long line, which goes in one direction only from the fixed point z1, but doesn't actually include the point z1 itself. It's called a half line, and the reason why it's called a half line will become clear in a minute. You get something like that. So it is an infinitely long line stretching from the point a plus bi, where theta is the angle made between the line and the positive real direction, the positive real axis. And it starts here. It is infinitely long, but obviously there is nothing to the left-hand side here, which is why it's called a half line. And the other slightly curious thing about it is it does have no start point. It doesn't include the point itself, because if you only had the point, then you wouldn't have an angle, you wouldn't have theta at all. So it stretches indefinitely far towards the right, and it stretches indefinitely far towards that point without ever quite reaching it. Okay, to find the Cartesian equation of a half line corresponding to the argument of z minus z1 equals theta, we do the following. So we start just with the definition of the locus itself, and then z is a general point, x plus yi, z1 is a fixed point where you know a and b. We substitute those in. That gives you that. Then we collect together the real and the imaginary parts, which gives you that. And then we use the basic definition of how you find the argument in the first place, which is that the tangent of the angle is equal to the imaginary part, y minus b, divided by the real part, x minus a. Rearranging that gives us y minus b is equal to tan theta into x minus a, which is the standard form for a straight line, where you know what the gradient is. In this case, it would be tan theta, and you have a fixed point AB. More frequently, you'd see that written as y minus y1 is equal to m into x minus x1. Okay, we'll have a look at an example. It says, given that the argument of z plus 3 plus 2i is equal to 3 pi by 4. First of all, sketch the locus, then find the Cartesian equation of the locus, and then try and find z such that both of these things are true. And the first thing you need to be careful with is this isn't written in the standard form. The standard form should have z minus a complex number. Anyway, I'll let you have a go yourselves first. So pause the video, have a go, and then come back to me again when you're ready. Okay, let's have a look at this. So to sketch the locus, the first thing we need to do is write this in the standard form. It should be z minus z1. And it is important that we do write it like that, otherwise we get this fixed point wrong. So writing it in standard form gives us the argument of z minus 3 minus 2i. So the fixed point is minus 3 minus 2, not plus 3 plus 2. Now sketching that, minus 3 minus 2 is down here. The angle 3 pi by 4 radians is 135 degrees, coming anti-clockwise from the positive real axis. So that's the locus, a half line which starts at minus 3 minus 2. We're then asked to find the Cartesian equation of that line. Well, we'll use the method that we talked about before. So you start just by using the definition of the locus. The argument is z minus 3 minus 2i is equal to 3 pi by 4. And then z, and we frequently do this in this type of question, we write as x plus iy, just the general complex number. And that gives us the argument of x plus yi minus 3 minus 2i is equal to 3 pi by 4. Then we collect together the real parts and the imaginary parts, which gives us that. And then we use the basic definition of what the argument is. So the imaginary part, y plus 2 divided by the real part, x plus 3, is equal to the tangent of the angle, tangent of 3 pi by 4. Moving the x plus 3 to the other side, the tangent of 3 pi by 4 is minus 1. So we get y plus 2 is equal to minus 1 into x plus 3. And rearranging that gives us y equals minus x minus 5. Now it is just a half line, so we do need to say that x has to be less than minus 3. Can't actually equal minus 3, but it can be any value less than minus 3. Part 3 asks us to find z such that the modulus of z plus 3 plus 2i equals 10. And as well as that, the argument of z plus 3 plus 2i is equal to 3 pi by 4. Now the second thing here is what we've just done. So that's the argument of z plus 3 plus 2i is equal to 3 pi by 4. What about this? Well, this is one of the standard loci that we looked at a couple of lessons ago. The modulus of z plus 3 plus 2i equals 10. Again, that would need to be rewritten as z minus 3 minus 2i is equal to 10. And that is a circle with center minus 3 minus 2 and radius 10. Drawing it, it would look something a bit like that. And what we're looking for is z such that both of those things are true. So what we're looking for is z here, which lies both on the circle and on the half line. Now, if you have the textbook, there's quite a neat geometric way of working out what that point would be, but it wouldn't work in all examples. The general method for doing this type of thing is to get the equations of the two loci and then solve them simultaneously, just like you would do if this was a normal graph. Now, the equations of the two loci are, well, the half line we worked out just now, that's y equals minus x minus 5. And the equation of the circle will be x plus 3 squared plus y plus 2 squared is equal to 10 squared. And we just solve these simultaneously. So we'll substitute y from the first one into the second one, and that'll give us that. Multiplying out the brackets, or tidying things up first, gives us that. Then multiplying out the brackets gives us that. Tidying all of that up, we get the quadratic x squared plus 6x minus 41 equals 0. And if you use the quadratic formula, then you get x equals minus 3 plus or minus 5 root 2. Now, if it wasn't a half line, if it was a whole line, there would be two solutions. The only solution that actually exists, you can tell by inspection, is the one where we have the minus 3 minus 5 root 2. If you take the positive value, then you'll be on the other side where the half line doesn't actually exist. So that's the value of x. To find y, we just substitute that into there, which gives us that. And tidying that up gives us y equals minus 2 plus 5 root 2. So the answer is z equals minus 3 minus 5 root 2 plus minus 2 plus 5 root 2 times by I. Okay, that gets us to the end of the lesson. And if you have the textbook, turn to page 52. And you can now do all of the questions from exercise 4A, but questions 10 to 19 are the ones that we haven't looked at so far. Thank you very much for listening, and cheerio.